chemistry. So we have graphs that show the potential energy versus the distance between atoms. That helps us describe the interactions between these atoms. So these graphs illustrate both the bond length, which is the separation between the atoms at which the potential energy is the lowest, and the bond energy, which is the amount of energy that's required to separate the atoms. It's important to note that the bond length will vary depending on the atomic radii of the atoms. So here are two graphs to show you. Notice how they both have a big dip under zero. So underneath the zero, those are the attractive forces, and above zero are the repulsion forces. So they're attracted when it's below zero, and they're being repulsed when they're above zero. So when they're too far apart, the energy is right around zero. But then as they start to get together, they get to this dipping point, which is the equilibrium point. And that is where, when it starts to turn up, then we know this amount of energy right here is called the bond energy. And so it goes down so far, there's a number associated with that. Then from zero, that is also telling us the bond length. So that's the distance between the two nuclei of the two atoms that are bonded together and how long that bond is. So for hydrogen, in this graph, the bond length is 74 picometers. Then up at the top, do you notice how they're too close together? They're kind of right on top of each other. And so they are going to repulse each other because they're too close. The electrons are going to repulse against the other electrons, and there won't be a good bond. So that's very unstable, and that takes hardly any energy at all to break that apart. Okay, so you have to get into that happy medium area. This picture on the right is also a graph showing this, but it's with an ionic compound. And so it shows the pink line shows the repulsive interactions, and the green line shows the attractive interactions. And the total energy kind of follows the attractive at first, and then it goes to follow the repulsive after it hits that sweet spot where that tells you the distance down, tells you that it takes negative 558 kilojoules per mole of sodium chloride to break it apart. And then this distance here is the bond length. Okay, so these graphs are nice because they help us to show where is that happy medium, where's that spot where they're not too far away, they're not too close, the two atoms or ions are in that perfect sweet spot. Coulomb's law can be used to understand the strength of interactions between cations and anions. Because the interaction strength is proportional to the charge on each ion, the larger charges lead to stronger attraction. So that means sodium chloride has a weaker attraction than magnesium oxide. And that's because sodium has a +1, chloride has a -1, magnesium has a +2, oxygen has a -2. So the higher the charge, the stronger the attraction, because the more electrons are being transferred in that bond. This would also work if you did sodium chloride versus magnesium chloride. Because the magnesium has a +2 charge, that is going to have a stronger attraction. Okay? We can also look at it by their locations on the periodic table if they have the same charge. So because the interaction strength increases as the distance between the centers of the ions, called the nuclei, decreases, smaller ions lead to stronger interactions. So lithium is a lot smaller than rubidium, the Rb. It's higher up on the periodic table. So because it's smaller, that has a stronger interaction. And that has to do with the fact that it is smaller. And so it can fit into tighter places compared to larger atoms or larger ions. That's hard for it to stay with other large ions. So knowing how larger charges lead for stronger attractions is important to remember. In our textbook, this energy that we're talking about is called lattice energy. So there's some more information about the book in the book at those pages. There are many factors that influence the stability and the structures of binary ionic compounds. We know that ionic compounds are formed from the transferring of electrons, so how strong the compound is can be determined by what's called its lattice energy, which is the change in the energy that takes place when separated ions are packed together to form an ionic solid. So those energies, the lattice energies, have been calculated based on experimentation that we are going to use those values to help us compare using Coulomb's law, different things. So here are some pictures of ionic structures with the lattice structure. So the lattice here on every corner is an ion that is lithium fluoride, and then the bottom one underneath it, that is just a space-filling model of the same thing. So it's just not spreading out the atoms, it's putting them all together for you to see. Then we have sodium chloride over there packed in. Notice how the positive and negative ions are they're like, what's the word for that? You know, they're alternating. That's the word I was looking for. So they're alternating, they are staying apart, the positives aren't by the positives, the negatives aren't by the negatives, and that all has to do with those attractive and repulsive forces with the nucleus and with the electrons. So they're trying to make it as stable as possible by alternating their formation. The greater the ion charge, the stronger the lattice forces. So that means the higher the melting point of the solid will be. So when it has a higher energy, that means it takes more energy to break it apart, to break those bonds that are holding it together. And that's why ionic compounds have the highest melting points, because those are the strongest bonds. Answer the following questions related to the chemical bonding in substances containing chlorine. So this is taken from an AP question that partly relates to what we're talking about. So in A, what type of chemical bond is present in the Cl2 molecule? Well, the Cl2 molecule is just a bond between two chlorines. Okay. Well, we know that they are, since there isn't a metal present, it's going to be covalent. So it's going to be a covalent bond. And since they're both the same element, we know that when they're the same element, that would form a nonpolar covalent bond. So you might want to take some extra notes, because the difference between a 2 and a 3 is explaining yourself in more detail. So you might want to say, this is nonpolar covalent because bonding two of the same type of atom together makes a nonpolar molecule because all of the electrons are being shared equally. Something like that would be fine. B, Cl2 reacts with the element Sr, which is strontium, to form an ionic compound. Based on periodic properties, identify a molecule called X2 that is likely to react with strontium in a way similar to how chlorine reacts with strontium. Justify your answer. Okay, so when it says periodic properties, it's talking about where close to it on the periodic table, that's where you're going to find what element replaces it. Okay, so chlorine, when it interacts with strontium, it has a -1 charge. So you're going to want to look in the same column, the same pillar, the same family, to pick this molecule. The best one, I would say, would be for the F2 molecule, the fluorine molecule. And that's because it's in the same column, so it has the same number of valence electrons, and same number of valence electrons, and it's actually more electronegative. So that means it's going to want to gain the valence electrons from strontium even stronger, even better than the chlorine does, because it's more electronegative. It wants all the electrons it can get, and so strontium has 2 that it could give it. So that would be my choice, would be that fluorine is a good one because it has the same number of valence electrons, it's in the same family, they're both halogens, and fluorine is more electronegative, so it will react very similarly to how chlorine reacts. All right, last one. A graph of potential energy versus internuclear distance for 2 chlorine atoms is given. On the same graph, carefully sketch a curve, that corresponds to the potential energy versus internuclear distance for the 2 bromine atoms. Okay, well, so we know, I'm gonna erase this, but we know that this dip here is the amount for the bond energy, and we know that the distance here is the bond length. Okay, well, looking at the periodic table, bromine is lower than chlorine. It's the next one down from chlorine. So that means that chlorine is bigger, atom-wise, the atomic radius of bromine is larger. So bromine is bigger. Okay, so because it's bigger, then that tends to make us believe that the distance between the 2 atoms, the internuclear distance, is going to be slightly larger than the chlorine. So that tells me that, and I'm going to do this in a different color. Let's pick blue. So that tells me that I'm going to need my bond length to be a little bit farther to the right for the bromine. Okay, because I know that bromine atoms are larger than chlorine atoms. And when you have a bigger atom, then that means that it's going to be a weaker attraction. So the energy will be slightly less. So that means that I also need this dipping point, the equilibrium point at which that's the perfect amount, needs to be a little bit higher. Okay, now this isn't going to be perfect. I am not an artist, but this is just sketching where you think the curve could correspond. So we know that it needs to be, that sweet spot needs to be slightly to the right of where it is now, and it needs to be slightly higher. So drawing my line in, I'm going to have that for my bromine sketch. Is it perfect? No. We could make it more perfect if we had experimental data, but we're not given that here. So we are just trying to use our Coulomb's law knowledge to draw that for ourselves. All right? So that is 2.2.